The first step in logical database design is to simply more or less mechanically turn the ER diagram into a set of tables with primary and foreign keys. The second step involves cleaning up this initial set of tables through a process called normalization. In general, if you created a good ERD and mapped it into a set of logical tables following the rules that we covered in the previous lectures, the tables in the logical database design will be well structured. However, in some cases, you need to clean up the tables through a process called normalization. This lecture covers normalization, and at the end of the lecture you'll be able to explain the importance of normalization, explain the concepts of first, second and third normal form, and normalize a database design up to third normal form. Normalization is a methodology to create well-structured tables. A table is well structured when it contains minimal data redundancy and allows users to insert, modify and delete rows in the table without errors or inconsistencies. A well-structured table contains information about one and only one thing in the model. If a table is not normalized, we may suffer from insertion, update or deletion anomalies. An insertion anomaly occurs when we can't store some data because we don't know the value of another field or fields. For example, the table on the slide combines information on orders and customers. As we shall see later, it violates third normal form. The issue is that we may want to record information about the customer even before they've placed an order. And since order ID is the primary key, we can't insert a row in this table if we don't have a value for order ID. Update anomalies occur when we have to change values in multiple records to correct the value of a single field. So assume that the customer can place more than one order. If a customer now changes their address, we will have to update the value of customer address for all orders placed by that customer. Deletion anomalies occur when the deletion of a record results in the loss of pertinent information. For example, assume that the customer has placed only one order. If for some reason we want to delete this order, we also lose information about that customer. So, normalization, as we said, is the process of creating well-structured tables that are relatively free from insertion, update and deletion anomalies and which have minimum data redundancy. Normalization is done in layers. For example, to ensure that the table is in second normal form, we first have to make sure it is in first normal form. And there are a large number of layers, as the following indicates: first normal form, second normal form, third normal form, Boycott normal form, fourth normal form, fifth normal form, domain key normal form. However, for the purposes of this course, we will restrict ourselves to the first three. In practice, it's almost always sufficient to make sure that all the tables in a logical design are in third normal form. And this is in fact the industry standard. Normalization is the process of discovering and removing undesirable functional dependencies. A functional dependency arises when one attribute determines the values of other attributes. For example, a social security number determines a person's name, address, birth date, phone, and an ISBN determines a book's title, author, subject, and so on. Good or full functional dependencies occur when all the fields in the table are functionally dependent on the full primary key. For example, in the employee table, all fields are functionally dependent on the primary key SSN. Bad functional dependencies are ones in which some fields are not functionally dependent on all the fields in the primary key. For example, in the project table, while start date and end date can only be determined if you know both the project and the employee, you can know the name of the employee if you only know the employee ID. There are three criteria that a table has to meet to be in first normal form. The first criterion is that each attribute is atomic. For example, a name attribute in an employee table is likely to consist of multiple elements such as first name and last name. The same holds true of the address attribute, which is likely to consist of a street number, a street, a city, a state, and zip code. We resolve the issue by decomposing the non-atomic attributes into its constituent components and storing the components as separate attributes in the new table. The second criterion that a table must meet to be in first normal form is that each attribute in a row must have a single value. The example below shows what happens when we incorrectly map a one-to-many relationship. As you see, the EID encodes the business rules that the salesperson may sell to any number of customers, but that the customer is associated with exactly one salesperson. You will also recall that the correct way to code this up is to make the primary key of the one part a foreign key in the many part. If we do it the other way around, as I did below, we end up in a situation that violates first normal form, since customer number in salesperson has multiple values, one for each customer that the salesperson sells to. The third criterion that the table must meet to be in first normal form is a generalization of the second criterion, and states that there should be no repeating groups. Thus, in the example, there are repeating groups to record that an employee has passed the course. The solution is to separate the table into two new tables and create a relationship. So this is the solution to the violation of first normal form on the previous slide. You see that we created two separate tables, namely employee and course completed, and that we established a relationship between the two because employee ID, the primary key in employee, has become part of the composite primary key of course completed and therefore is a foreign key in this table. In order for a table to be in second normal form, it must be in first normal form and there should be no partial dependencies. Partial dependencies occur when the primary key is composite and certain attributes are determined by part of the primary key and not the entire primary key. This is in contrast to full functional dependencies in which every attribute is determined by the entire primary key. This example shows a violation of second normal form. While the date completed field is functionally dependent on the full primary key, i.e. you have to know both employee ID and course to know the value of this attribute, there are partial dependencies between the attributes employee name, department, salary and the primary key. As you can know the values of these attributes if you know the value of only the emp ID field in the composite primary key. As was the case with the violation of first normal form, we could solve a violation of second normal form by decomposing the offending table. As you see, we created a new table employee, which is primary key emp ID, and we moved all the attributes that had partial dependencies in the original table into this new table. The other table, emp course, retains the composite primary key, but now only contains the attribute that had full functional dependency on the original primary key. In order for a table to be in third normal form, it has to be in second normal form, and it should not contain any transitive dependencies. Transitive dependencies occur when there are functional dependencies between attributes that are not part of the primary key. This example is a violation of third normal form. After all, the value of manager ID allows you to determine the value of manager name. As before, the solution is to decompose the table into separate tables. So in the example below, we move the attributes with the transitive dependency into a new table and make the primary key of this new table manager ID, a foreign key in the table from which we removed the attributes. While normalization is normally the right thing to do, you need to use some discretion. Normalization may lead to too many tables, which may affect processing efficiency, for example for queries that combine data from multiple tables. So you should not go further than third normal form, which is the industry standard anyway. Also, there is no need to normalize for fields that are unlikely to lead to anomalies. For example, In an address, city is functionally dependent on zip, and most tables that record city and zip therefore technically violate 3NF, the third normal form. However, there's no real need to normalize, as this situation is extremely unlikely to lead to anomalies. Finally, keep in mind that anomalies occur only in databases which change. So denormalization, or not normalizing, is fine, for example, for data warehouses. To check whether a set of tables is normalized, you can use the following checks. Ask, do any attributes have multiple values for a single instance of an entity? If so, remove the repeating attributes and groups by creating new tables and creating relationships between them. If there aren't any multi-valued attributes, then the table is in first normal form. Then ask, is the primary key composite? And are there any attributes functionally dependent on only some of the primary key fields? If yes, then remove the dependency by creating new tables and creating relationships between them. If not, the table is in second normal form. Finally, ask, are there any functional dependencies between attributes other than the primary key? If yes, remove the dependency by creating new tables and, if necessary, creating relationships between them. If not, the logical data model is in third normal form.